Hello everyone, my name is Austin Huang, and my group will present our project on machine learning in Unity. Our motivation for choosing reinforcement learning is that it is a hot topic in the field of AI and machine learning. We wanted to get a close look into how it worked and apply it to one of the significant challenges we faced in the race car curriculum. This project also gave us an opportunity to explore various advanced features in Unity. Our objectives were to create an ML environment and train our race car to navigate through a ConesRL course. We used 4 stages for this training process. In the first stage, we had a simple straight line of 4 cones alternating between red and blue. In the second stage, we introduced the curved layout. In the third stage, we had a randomly curved layout to help the code and the car be more robust. And in the fourth stage, we tested it on the Phase 1 Challenge course.
Hello, I'm Steven, and before we go deeper into what we actually did, let's explain some of the brief concepts and methods and tools that we used in our machine learning model. A big thing was reinforcement learning, and this is essentially, you can think of it as a free-for-all where we sort of let our robot just drive around and figure things out. And the way we make the robot learn is by feeding it rewards. So if we want to pass a blue cone, let's say to the left, we would give the robot a positive reward for that, and we would give it a negative reward if it does the undesirable thing, which is passing the blue cone to the right. And this ultimately helps the computer distinguish, what is something that we want to do, which is what is something we don't want to do. And the ultimate goal is to keep doing things that will lead to what we want to do, right? Now, on top of this reinforcement learning, we also use a neural net. And what a neural net basically does is that it takes in all the information that we collected to reach a certain action. And it does a bunch of mathematical calculations to give us a final action that we want to do. Basically, we have these weights, and we want to sort of emphasize actions that lead to a high reward, right? Because a high reward means that we're doing what we want. And ultimately, as more information is spoon-fed into the neural net learns that like certain weights are going to be emphasized and certain weights are going to be less emphasized, right? And ultimately, this allows the computer to understand information that's valuable versus information that's not valuable.
Hello, I'm Daniel, and I'm going to be explaining some critical decisions that we made regarding the implementation of our reinforcement learning project. First, I want to talk about ML agents, which is the framework that we used in order to train our actual model, so it's super important to our project. What exactly is ML agents? It's a package that allows you to communicate between Unity and Python, but more specifically, it allows you to control the decisions of a character in Unity, in which case we're doing a race car, and train it upon a Python neural network framework. We're using PyTorch. So this was just too perfect not to use, It's a very efficient, very pragmatic type of setup, and our simulator was actually built in Unity, so we just decided to stick with it. So now that we had a machine learning framework, all we had to do was run something on that machine learning framework. So we used something called PPO, Proximal Policy Optimization, which is a type of policy gradient which helps maps actions to states in a reinforcement learning scenario. PPO was already kind of pre-set up on ML agents, so all we had to do was actually run it and tune a lot of parameters, but once we got those parameters correct, it worked very well. It was efficient. It was easy to implement. It was good with continuous decision making, and it was very easy to tune. So overall, it was fantastic. We also used something called imitation and Gale learning, in which we would manually record a file of us running through the track, and then it would take that into account when it's training in order to kind of speed up the process, and it sped it up by quite a bit. And then finally, we used something called a curriculum style of training, in which we would train the model on an easy level, and then we would up the difficulty of the level, and then we would reset the learning rate, and then we would train it over and over, and then eventually we got to a rather difficult state. And so now we're going to be moving on to the results.
In our Unity environment, we started by using the color camera to train our model. However, after a few days of training, we realized that using the color camera wasn't the most efficient way to train. Instead, we started using raycasts, which are a modified version of LiDAR that allows the machine learning model to have simplified data about distance and the type of object it's looking at. After the first day of training with the color camera, the model was able to successfully go through 4 cones and reach the end. However, when the cones were structured differently, such as a different distance apart, the model failed. Because of this, we switched to raycasts, and the model was able to do much better, going through many cones with a randomized left and right and up-down value. This allowed the model to generalize the location of the cones to do better on conditions it hasn't seen before. On the 3rd and 4th day, the model kept training, and it was able to do curves in the cones. This allows it to go across bends like the one seen in the P1 challenge. By day 4, we were able to try our machine learning model with the P1 challenge. We were only able to get halfway with the current model because of some of the limitations with our training environment. This can be fixed with more training or with training specifically on the P1 challenge environment. At first, when training our model, it took a few 100,000 steps for the car to figure out a basic turn to go around the cone. After that, however, the car started learning much faster as it was able to generalize the steps for the other cones. We used the car's color camera at first, but realized that training took too long as the machine learning model had too much data to process. We switched to using raycasts, and the training process became much quicker.